This is an economics application. I want to talk about compound interest. Compound interest is when you earn interest on your interest. If you're saving for retirement, you would like your retirement funds to earn compound interest in order for them to grow fast enough so you have enough money after you retire. So let's work the mathematics of compound interest. So let's let S of t be the account value at time t. Let's assume we start with some money in the account. So S naught is the initial account value. And let's say R then is the annual interest rate. In a bank account, it's actually interest. In an investment, it's your annual rate of return from your investment. So let's see how compounding works. We have first the simplest type, which is just annual compounding. So for annual compounding, we have the value of the account at time t is the initial value, and then you get the initial value plus the interest you earned. So it's the initial value times 1 plus R. And then you earn interest after the first year. After the second year, you multiply again by 1 plus R. After the third year, you would have a 1 plus R cubed. So this would be a 1 plus R raised to the t power, where t is the number of years. Okay, we can do better than annual compounding. We can compound, say, twice a year or once a month. We can do often frequent compounding. So let's just say we do compounding n times per year. Then what would the expression look like? So then we have the amount of money in the account at time t is S naught. Each time you earn interest, you don't earn R, which is the annual rate. Now you earn R divided by N, which is the rate you get for that period of compounding. And instead of getting it every year, you get it N times per year. So it would be raised to the NT power. And that would be compounding N times per year. Then from here, we can go to the limit. We can consider continuous compounding. So that corresponds to the limit where n goes to infinity. And then we have this nice result from calculus that the limit as n goes to infinity of 1 plus R over n to the nt power. You can remember this result by just remembering that 1 plus R over n are the first two terms in the Taylor series expansion of e to the R over n. And e to the R over n raised to the nt power is just e to the RT. So this limits to the exponential function. And then we get S of t then is equal to S naught times e to the RT. So you have exponential growth of your money. This grows very rapidly, which is why you want to have compound interest for your retirement accounts. There's another way to obtain this, perhaps a little bit more sophisticated, but we know how to do it now from calculus. We can ask how much money is in the account at a time t plus delta t. The amount of money in the account at that time is equal to the amount of money in the time t plus the interest that you're rewarded. So how much interest is awarded after a time delta t? That would be plus R delta t times the capital, which is S of t. So the amount of money at a time t plus delta t is the amount of money at time t plus the interest that that money receives in the time delta t. We can now look for a derivative in this equation. We can write this as S of t plus delta t minus S of t, and then divide through by delta t. And what do we get left over? We get an R times S of t. This looks like our definition for the derivative. So we can just put a limit here as delta t goes to 0. That gives us continuous compounding. And this reduces to the differential equation ds dt is equal to Rs. Our initial condition is S of 0 equals S naught. And that's our differential equation and initial condition, which gives us the exponential function. Let me summarize. This is, we're talking about compound interest. When you earn interest on your interest, we took a stepwise approach, annual compounding n times per year, until we got to continuous compounding and introduced the exponential function. Here we use a differential equations approach. We consider the difference equation for S of t plus delta t. We limit it to get the derivative, and then the derivative and the initial condition will give us the exponential function solution. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.